Welcome to the CFD Research Corporation presentation for the topic N19A-T020 STTR. I am Devashish Sengupta, PI of this project. In this presentation, I will outline our novel machine learning technology for accelerated discovery and design of materials for high temperature applications. This technology is especially targeted towards the programs related to propulsion and power. The topic author for this STTR is Dr. David Schiffler at ONR. In this slide, I want to give you an overview of our company history and capabilities. Our company was established nearly 35 years ago from the garage of our former CEO, Dr. Ashok Singhal. Currently, CFD Research has nearly 170 employees, of which a large percentage has advanced degrees. We have a track record of developing cutting-edge technologies for DoD, primes, and commercial industries. Modeling and simulation at multi-scale level coupled with design, fabrication, test, and evaluation is what that separates us from the other companies. We also provide expert support services. We have a track record of transitioning technology into the market. More than 20 technologies were transitioned to the market and 3 companies were spun off. We have protected our technology with awarded and filed patents. We are located at the Research Park area in Huntsville, close to Redstone Arsenal, Missile Defense Agency, and NASA. Let us talk about the challenges and interest of Navy. All power and propulsion systems have turbine engines. These engines are located in Navy ships and aircrafts. Next generation ships and aircrafts are expected to have increased payload capacity, higher flight speed, greater range, and shorter response time. In order to achieve these goals, turbine engine efficiency must be significantly enhanced over the state of the art. Efficiency of a turbine engine is highly dependent on its operating temperatures. Engines that operate at higher temperatures are more efficient. However, higher temperature also creates a highly oxidizing and corrosive environment. Therefore, developing efficient turbine engines essentially is limited by the survival of the component materials in extreme environment. Refractory high-entropy alloys, which are known as RHEA, are thought to be a promising class of materials for fulfilling this objective. Transition targets of these technologies are various PEOs such as Aviation Common System and Commercial Service, Tactical Aircraft Program, Unmanned and Weapons. We expect that our artificial intelligence and machine learning based material discovery technology will accelerate the development of this class of alloys with desired properties. Let's talk how materials are developed for specific application. The process is performed primarily by material scientists and metallurgists. The figure outlines the general procedure for material development. Typically, heuristic knowledge of the material scientist and metallurgist plays a big role in conceptualizing alloy composition. Once the concept compositions are decided, they are processed in the laboratory. The processing includes ball milling, arc melting, annealing, etc. The processed alloys are then tested for their mechanical properties and oxidation resistance. If these properties do not meet the target requirements, new alloys are then again conceptualized and the process is repeated until the property requirements are achieved. Clearly, this is a time-consuming and expensive process. For example, average time for development to market for a material is approximately 20 years, which is too long in the 21st century. This must be reduced to 5 years or less to be ahead of our adversaries. However, no technology exists at this time which can accomplish this. Our AI ML driven technology has the capability to rapidly screen thousands of alloy compositions within hours and identify candidates that have potential to meet the requirements. This will essentially replace the bottleneck of experimental approach and dramatically reduce the time for development and risk of failure. In this STTR project, we have developed a sophisticated software tool based on the state-of-the-art AI/ML techniques. We also created a property database by painstakingly collected data from various journal articles. This database was used for training machine learning models such as neural network, random forest, gradient boost, etc. The developed models were then verified against experimental data supplied by our collaborators. The models include predictions of material strength, plasticity or ductility, and oxidation resistance. These models are then used for discovering new alloy compositions in two ways. It can be used for improving the properties of a known alloy by coupling with an optimization algorithm. You can see the procedure is shown in the figure. One can request the optimizer to discover an alloy composition with a set of target properties. The algorithm intelligently and automatically navigates through the composition space to arrive at a composition satisfying the target requirements. In the second approach, the machine learning model can be used to generate hundreds of thousands or even millions of alloy compositions and their properties using high throughput technique. Mapping them on a 2D surface will guide the experimentalist to search an area where chance of success is maximum. The key innovations of this technology are the rapid identification of potential candidates and its ability to predict alloy composition to meet requirements for a target operating temperature. So far, our work has progressed very well, and we are confident that the TRL will be at least 5 at the end of the phase 2. The table in this slide gives an overview of the status of the project. The TRL column shows changes in the overall TRL of the technology as we progress in time. Clearly, as we add more capabilities, the overall TRL goes up. The basic code development with optimization algorithm is complete. The code is now being used for incorporating various property models. Development progressed well and successfully completed in December 2020. Development of yield strength model is complete now. The model is performing very well. We are now using it for optimization and high throughput search. Model validation is also complete. Next, we developed a ductility model. Although it was difficult, we now have a model that is adequate and reliable. We are using the model to perform material screening. We also completed model validation. Next, we developed a model for oxidation resistance, but it requires some improvements. We now have a sufficient experimental data from journal articles. This will be used for further improvement of the current model. We are also doing implementation of the last milestone in parallel with other developments. This will combine all models and algorithms into a complete toolkit. This slide shows some of the results that we obtained from our R&D work. We have used the codes and algorithm discussed in the previous slide. Figure on the top left shows the experimental versus predictions of yield strength using the model developed by us. The results show excellent prediction of yield strength both at room and high temperatures. As you can see, the correlation coefficients of prediction is close to 90%, which indicates that the model is of high quality. Next, we coupled the yield strength model with an evolutionary algorithm to identify a composition that maximizes yield strength. The starting alloy, hafnium, niobium, tantalum, titanium, zirconium, is shown in the right bottom of the slide. This alloy has good ductility but has low yield strength. Our machine learning and optimization algorithm is able to find composition that significantly improve the yield strength at room temperature and 1000 degrees centigrade. Figure at the top right corner shows the temperature dependent of the alloy composition optimized at room temperature and 1000 degrees centigrade. Experimentalists often like to see such temperature dependent plots to assess the goodness of an alloy for high temperature application. Overall, I can say that our progress towards achieving the technical goal is excellent and we are on schedule. Code is fully functional and it can be used by interested parties with some training. So, if anyone is interested, feel free to contact me. The features and the benefits for the AI/ML software is that it can derive knowledge from a large number of data, which is very difficult by manual inspection. The process facilitates rapid screening of materials. The models developed in this work were also validated against experiment, therefore can be applied with confidence. Application of the validated models will significantly shorten the time to market for new alloys. Finally, the software is easy to use and can be used by non-expert with some degree of training. User can specify target properties and the software is capable of finding right compositions through optimization. It can benefit in developing high temperature alloys for increasing the efficiency of gas turbine engines. As we complete the phase 2 base period, we are looking for government programs for transitioning the technology. Our initial research indicates that several PEOs within NAVAIR and NAVC can use our technology. We are very interested in talking to these PEOs. Materials for extreme environments such as hypersonics are also of interest to MDA, Army, and Air Force. We would be very interested in talking to the PEOs of these agencies. NETL within DOE is also working on developing high temperature materials for industrial power plant applications. We have seen some interest from NETL about our software. We will explore this avenue further. We are also looking for interested industries for licensing our technology. So, if you are interested in reducing the time to market for high temperature materials, we can help and we will be very interested in talking to you. For transition and partnership, we want to say that our product can help in accelerating the development of high temperature materials. We want to work together with material scientists and engineers to achieve this goal. So, in this STP meeting, we are looking for contacts within DoD and industries who can partner with us and explore the capabilities of our technology. Since the tool developed under this STTR program is quite general, it can also be used for other materials such as superalloys, shape memory alloys, and energetic materials such as propellant and explosives. So, again, we want to talk to you. We want to know more about your challenges and we want to work with you. Here is our contacts. Myself, Devashish Sengupta, would be very happy to answer any technical questions. For technology transition and business related questions, Vincent Harand and Ashok Raman would be very happy to talk to you. In the end, I want to say we believe in the power of collaborative efforts. By working together, we can progress as a team and solve some of the today's challenges. Thank you for your attention and I would be very happy to answer any questions you may have.